I'm Tim Wood from George Washington University. I'm faculty there. This is work that I did with my student, Zhang, as well as KK Ramakrishnan and Jinho Hwang. So I'll be talking about our SmartSwitch platform, which is, as he says, kind of blurring this vision of what is your network, what are your applications, and how can we kind of mix those together in interesting ways. So as I'm sure you all know, networks are really changing. So the scale of our networks is getting bigger and bigger as we build these massive data centers, as we build out the WAN to support more mobile users. So we have very large scale networks. We have highly dynamic networks because our workloads are changing. Our applications are moving around the data center as we migrate them around. So there's a lot going on about inside the network. You know, it's not just a bunch of machines hooked up to a hub anymore. We have very complex topologies, complex network infrastructure. As part of that, we have had a lot of changes in the hardware and the control plane that are behind these networks. So I'm sure you've all heard of SDNs by now, this idea that we can have a centralized software controller to help manage our network and make it more flexible. There's also this idea of network function virtualization. I'll talk about that a bit more in the next slide. And here we're just saying we don't necessarily need hardware switches and routers anymore. We can do more of this in software. Maybe we can even do it inside virtual machines and try to get that flexibility into our network. So, you know, the networking hardware has changed quite a bit, right? We have, traditionally we've always used these hardware switches, hardware routers. These are single purpose, big boxes that cost a lot of money. They're not that flexible, right? Even now that we have SDNs that can help us control these switches and routers, we don't have that much flexibility in how we use these different devices. So what I'm really interested in as a systems person is how we can make more software-based networking infrastructure. And there's been a lot of interesting work in the last few years to help us do this. So this goes back, you know, the last a number of years. So Packet Shader was one of the first systems to really show high-performance network processing inside a commodity server. They were using GPUs to help accelerate that. They could get about 40 gigabits per second processing rate. So that's actually pretty good to begin to be able to replace some of our real networking hardware. More recently, we've had things like NetMap and Intel's DPDK, Data Plane Development Kit. These are essentially just libraries that help you do zero-copy I/O. So you can move packets very quickly from your network card into your application that's just running on a regular commodity server so that we can do our network functions inside commodity servers instead of these special purpose boxes. Just in the last few months, so at NSDI, there were 2 papers about taking this a step further and saying, okay, we can actually run these network functions inside virtual machines themselves. So ClickOS and our work on NetVM, we're both at NSDI earlier, and they're just showing that we can eliminate the virtualization overheads and let you run line rate packet processing apps inside virtual machines themselves. And this is really what's going to give us very flexible deployment of services sort of whenever, wherever you need it inside the network, and then maybe we can compose these virtual machines to build even more interesting network services by grouping them together. So there's lots of problems and opportunities here, right? We have these very dynamic workloads, these ever-changing applications, these users that are sort of moving all over the place, and applications that are moving around the data center in response to that. So the network really needs to have greater flexibility than it does today to adapt to these changing conditions. The other issue is that network is really becoming more than just a transport mechanism, right? We don't just use the network to move a packet from point A to point B. The network is providing other services now like security, quality of service, monitoring or management systems, your accounting, you can have caching, CDNs inside the network, video transcoding. All these things can be built into the network themselves. So the network really needs to be powerful to do more than just move packets around. So we kind of view this as an opportunity to rethink what we view the network as and what we view our end host applications as, and how we can sort of begin to merge and integrate these two together. And we really think that virtualization is what's going to provide the flexibility, the efficient resource management, and this greater power about what kinds of applications we can embed inside the network themselves. So here's an outline of where we're going. I've given you some motivation, talked about high-performance networking in VMs. I'm going to describe our SmartSwitch platform that we're working on putting together now, and talk about some of the use cases that we think this will be most useful for. And I'll give you a bit of preliminary results for what our system's capable of. So the first example Okay, so first let's start about what this platform actually is. So it's built upon our NetVM platform, which is a virtualization platform designed for high performance networking. So each of our different virtual machines is going to be running a different component of a network service or of some kind of application. And we can do everything you normally do with a virtual machine here, right? We can allocate resources to these on the fly. We can run multiple virtual machines on one host. So in this figure on the left, we see a couple different NetVMs, a couple different virtual machines running network services, and they each have different resources. One might have some special storage, one might have extra CPU capacity, another one might be a memory-focused virtual machine. So depending on what your network service needs, we can very easily assign it the resources that it's going to need. And then we can have some kind of virtual machine flow director that's going to help move your packets to the virtual machine that it needs to go to for whatever network service you're trying to build. So this can assign your incoming packets to VMs using very flexible rules, right? This isn't just hardware that's predefined to have a lookup table. This is any kind of software you want to write that can use very complex rules to decide how to move packets around in this system. And again, we can combine these different virtual machines to build even more complex services on top of it. So we've got some big data center with some interesting topology, and now we can start running these different NetVM hosts throughout this data center, some on that regular end hosts, some on different switches at different levels in this network, and we can start running our applications or our interesting network services wherever and whenever we need them. So the first use case that I'll talk about is if you have a very large-scale Memcache deployment and you're interested in working on the load balancing to send your requests to these different Memcache nodes. So you probably all know that Memcache is a very easy to use and efficient key value store. So it's used by most of the really large-scale web applications. And the nice thing about Memcache is you can just start a whole bunch of these nodes, and then you can just shard your data, spread your data across all your different Memcache servers. Typically, you'll then use something like consistent hashing to decide which request should be routed to different servers. So now you need something that actually knows this mapping of keys to servers. So this could be a proxy. You might run this on a sort of a centralized machine, and here we should see the different web servers send a request to the proxy. The proxy looks up where that key is supposed to be located and sends it on to the Memcache node. So this is convenient, having sort of a centralized load balancer. If you want to change your mapping of where keys are or how many Memcache nodes you have, it's simple to update this proxy and sort of rebalance your Memcache cluster. Of course, the problem is you've got a centralized proxy. It might get overloaded very easily. It's going to be adding some latency to each of these requests. So often people push this proxy onto the web servers themselves. So they each run their own little proxy, which helps them determine which servers to send to. That gets rid of some of the performance problems, but now you don't have this easy to update mapping anymore, right? Now if we want to change how many Memcache servers we have, or we want to do something smarter about which keys are allocated where, we need to modify all of these different proxies, which may have some consistency issues for us. So the kind of thing that we're proposing is just saying, look, there probably is some switch between your web server and these Memcache nodes. Let's make that switch a little bit smarter. Let's make that switch able to look at the packets that are coming in, and instead of just routing them based on the MAC address or the IP address that they're destined for, let's have the switch look inside the packet, see what key is being requested, and automatically forward it to the correct node. And if we can do this in a very efficient and scalable way, we'll have this benefit of sort of a centralized load balancer, but we won't have the overheads incurred by existing proxies and load balancers. And we might be able to do some smart things like have the return path avoid this smart switch so that we can do this even more efficiently than the load balancer would normally be. Okay, so what this is really getting at is just saying we've got these network components like switches and routers. Let's start embedding some of the application knowledge that we have inside these switches to make them smarter and make them more powerful about how they handle the incoming traffic. And of course, the benefit of using virtual machines is that this gives the person designing this network service a very familiar environment. They're just writing regular code. Each of our virtual machines are isolated from each other, so this is really important in a data center environment where we probably have many different applications, many different users, all sharing this network. So this way we can have different VMs different network VMs that are assigned to different users, sort of handling each of their flows individually, so that we can have very different, we can have networks that are giving completely different features to different users because we have a very easy way of assigning VMs to the different application paths going through them. And by having this, by grouping these VMs inside an individual host, we can route requests through them to build up interesting services. Maybe we've got a generic intrusion detection system, but then an application-specific load balancer and an application-specific cache, all kind of built into this switch without even the application needing to know that these components are deployed inside the network. So if we can do computation in the network, we can do routing in the network, well, we can put other things in the network too, right? We can look at integrating some of our storage inside the network itself. So with traditional hard drives, that's probably not a great idea because they're so slow, but we're getting faster and faster storage. We've got these PCI Express SSDs, we've got new non-volatile memory technologies coming out, which can actually get speeds close to the 10 gigabit per second line rate of a fast network interface card. So you might imagine having a Hadoop cluster spread across a data center. You've got some tree network connecting these different nodes, and Hadoop does its best to do local computation locally on the data, but sometimes it has to move data from one part of the network to the other. So what happens if we can start integrating storage inside these network switches? We can have some kind of cache, some kind of disk prefetcher that's pulling data across the network and then keeping it locally where it'll best service those different end host applications that would like to make use of it. The basic idea here is just thinking that storage doesn't need to be at the end, the leaf nodes of your network anymore. We can push storage up to different areas and then think about how applications can best make use of that. And that's something that we couldn't do with traditional network hardware, right? You really need a flexible, general purpose commodity server-based networking system if you want to take advantage of these kinds of things. So the last example I'll give is sort of a wide area or ISP type network system where we can also think about using this kind of platform. So here we've got a bunch of cell phone users, maybe they're recording videos or watching videos from the internet. They're connected to a cell tower and then it's sending this data or retrieving this data from different data centers. So what we can think about here is that we don't really need all of that data to go all the way to the data centers before it's processed. We can now think about pushing some of this computation closer to where it's occurring. So we can have things like video transcoding happening right at that cell tower if we just have a few machines that are sort of integrated with the switches and routers that are already there, or we could have caching being performed at these different points in the network. And the important point here is that because this is all based on commodity servers and based on virtual machines, we can be dynamically starting these services wherever they're needed. We can move them around to different parts of the network, and we can replicate them as they're needed. It's really this greater flexibility that's provided by a VM-based networking infrastructure that's letting us do these things. So let's take a look at the prototype that we've started building for this. First, I'll give you a baseline that we compare against. So what our prototype does is it handles this memcached load balancing example that I gave you, trying to build a switch that has some application knowledge inside of it. And we compare this to the 2M proxy. So this is a proxy released by Twitter. And here's how that proxy works. You would have a web server. It sends a request to another node that's running the 2M proxy. This packet has to go to the kernel on that server. It gets sent up to user space where the 2M proxy looks at it. It figures out what you're trying to request, creates a new connection to your Memcache server, makes that request, eventually sends this back to the web server. So this can be pretty expensive, right? There's 4 packet copies between kernel space and user space just inside this proxy node, as well as the 4 DMAs to move your packet between the network card and the kernel's memory space. So this works, but it has high cost. With our MemSwitch, what we have is that we can reduce these costs quite a bit. So the web server just sends out its request. Our MemSwitch intercepts this packet that's coming through, it's able to look inside the packet and find the key that you're trying to access, and it'll just rewrite the data for that packet to change the destination address to the particular Memcache node that you're looking for. And because we're using our NetVM platform to run all this, we get zero copy packet I/O, and there's no added overhead for moving this packet between the kernel and this virtual machine. As soon as it gets DMA'd from the network card, the Memswitch virtual machine is able to access the memory where the packet is located. And then we can set this up so that when Memcached responds to the request, it actually sends it sort of straight back to the web server without having to go through our Memswitch virtual machine for a second time. And another nice feature that we can add is because this is all software, we can put anything we want in there. We can also test out adding a small cache inside of our Memswitch virtual machine so that this node is not only acting as a proxy, but it's also acting as a fast cache in front of the bigger Memcache cache. So we can see the performance of that as well. So here was our initial results that we got for this. So we're looking at the throughput of some different approaches for connecting to your Memcache servers. So if you go through the 2M proxy, you get about 100,000 requests per second. That's actually slower than trying to go directly to the Memcache node. So the proxy is adding a lot of overhead. And that's why generally the proxy is run locally on each of these web server nodes instead of trying to run a centralized one. With our Memswitch platform, we do quite a bit better, so about 700,000 requests per second. But this was our initial results. This is unfortunately what's in the paper. We have improved this quite a bit, so we really didn't even need to change our code that much. We just have a better test bed to really be able to test how fast this can go now. So these are our updated results. We can get 10 million requests per second using one CPU core and one 10 gigabit per second NIC. So we're sending out 10 million requests from our load balancer to these different Memcache nodes, which is pretty good. That would allow you to have one of these servers acting as a proxy for a pretty large Memcache deployment behind it. And I think that's what would give us the ability to have a switch which can be managing the mapping of keys to Memcache servers very easily. Here we'll look at some of the other overheads. So on the left, we have the latency of requests using these different approaches. So if you're going directly to a Memcache node, it's about 175 microseconds to make that request. With our Memswitch, it only goes up to 208, so we're not adding that much overhead to each of these individual requests. Of course, if we have our Memswitch set up to have a cache for some of these hot pieces of data, we can respond directly to the client within 19 microseconds. So we can have a very fast cache built into our switch just by adding a little bit more computation complexity and a little bit of in-memory storage on that node. And we also see that since we don't have to send the values that you're requesting back through our switch, as the value of the object that you're requesting is increasing, our performance stays roughly the same, whereas the 2M proxy is going to increase because it has to receive that full object and then send it back to the client again. So we've got pretty small overhead that we're adding, and it's not going to be affected by the value size. So to wrap up, what we're really seeing is that networks are just, because of the applications we're running and the users that we have, they're becoming more dynamic. So we need to figure out ways to add flexibility to the network processing elements and figure out things like where do we deploy different types of applications in different parts of our network services. So we're building this SmartSwitch platform based on very efficient virtual machine-based network processing and thinking about how we can then customize the network services that we're running for the specific applications that users are running inside the data center. Looking at things like adding storage, adding greater computation to these network service virtual machines. And of course, taking advantage of the benefits of virtual machines that are easy deployment, flexible resource management. There's lots of challenges remaining. We're working on some of these things, and hopefully others will look at these as well. So things like, we really need to rethink how we're going to manage our data centers if we have a much more integrated connection between the applications and the network services, right? Right now, we can mostly manage these separately, right? We can think about the computation, we can think about the network, maybe we have to worry about the network bandwidth of different servers, but these are generally thought of as separate provisioning problems. But now we're going to have much more tightly integrated resource management systems that are observing both what your virtual machine workloads for your end host applications are, and for these different network services that are tightly coupled with those. There's also issues like what's the right programming model to best make use of these network service virtual machines. How do we make it easy for application writers to push some of their intelligence into the network and vice versa? So with that, I'll wrap it up. I think that this is an interesting area. I wasn't really a networking person until we started working on this kind of project. But because of these things like SDNs and NFV, there's a lot more opportunities for systems people to get involved with building better support into networks. So with that, I'll take any questions or comments.
I'd just like to remind everyone to make sure you state your name and affiliation before you ask a question. So I'll get started a little bit. So I was really curious. So now that we've got these VMs at all layers, and you touch on it, do you have thoughts about what do we do to deal with just understanding the amount of resource each of these has? And now that hypervisor, whatever it is, the admission control policy, how do we make that work? Do you have any thoughts about what that entails?
Yeah. So that's something that we're beginning to look at, is how do you really manage these complex networks, and some of it is the initial physical provisioning, right? We're used to just putting switches that are connected by cables. Now we're going to have real servers there, and we need to think a little bit about how much computational power might you need at different points of the network. And then, of course, once it's running, there's the dynamic management problem. And I think that'll be a hard, interesting challenge, especially if you think about these being deployed in cloud data centers, right? Because you've got many different users that all want to share this networking infrastructure. And the cloud has to give guarantees to different users while still making sure that one user can't completely overrun the network or reroute things in a weird way. So both the isolation and the resource management there, I think, are really important, difficult problems.
Hey, Cristian Lumezzano, NEC Labs. So I have a clarification question. In your SmartSwitch example, is the application, so the web server, aware that packets are going through a SmartSwitch?
So in this case, it has no idea.
So then how are packets redirected to the SmartSwitch? What if by default they wouldn't go through the SmartSwitch?
So the way we set it up is that the web servers, they just think that there's one IP address that represents the entire Memcache cluster. So they're sending to one IP. Our SmartSwitch is designed so that it intercepts all the packets destined for that IP. It rewrites them to go to the specific server that it should go to. And then for the return path, one of those Memcache nodes, they respond as if they were that one IP, but they can respond directly to the cloud.
So then in this case, the location of the SmartSwitch matters. So it's important if I put it somewhere where routes to that IP don't go through it, then it wouldn't work.
That's a good point, yes. So it does need to be properly located so that the network flows are going to go through this SmartSwitch. So things like SDNs can help us with that.
Right, exactly. Okay,
Definitely.
Thanks a lot.
This is Ritesh with VMware. One question is, if you look at the evolution of Memcache there and what they're doing with CouchDB, so have you all looked into services such as replication or load balancing within the Memcache?
Right. So you certainly can have smarter end hosts that will do some of this management within themselves rather than having the load balancer do that. Certainly that's a viable approach as well. I think we're mainly using this as an example at this point as one of the possible uses for this kind of thing. I'm hoping that all of you will think up better uses if you have this kind of network platform that really can be integrated with your applications. What are some other uses of that? But it's true that this can be done both at the proxy level or at the back-end level. All right.
So let's thank Timothy.